computers and are always on the internet already know that I posted the third problem set. It's due next Friday. And because there's not a whole lot to talk about, I'll skip the office hours this evening. I'm sure you all have a very important TV event to attend to. So far be it from me to ruin it for you. I rest my case. So it looks like I'll have to set up time to meet with the 7 or 8 of you who still haven't managed to see me after your midterm, sometime early next week. So stay tuned for that. I'm going to be out of town starting tomorrow morning until late Sunday night. All right. So we were talking about linear systems. We characterize them in the following way, summary form. Linear systems satisfy the superposition principle. That means if you take two input signals, x1 and x2, and linearly combine them with scalars, usually these are either real or complex. We, in general, allow them to be complex, unless all the signals we're dealing with are real and the systems are real, and therefore the outputs are real. So on the other side, we get the same linear combination of the corresponding outputs. If this is true for all input signals, and all scalars that you pick, then the system is called linear. One of the consequences of linearity is that if I take just one signal and look at the output, y, you know that if I scale the input signal by some constant alpha, the output gets scaled by the same constant. Okay? If alpha is 0, this property must hold for all alpha scalars. If you pick alpha to be 0, what does this mean? What does that make the input signal? 0. So if x is 0, then y, which is a function of x, again, we're talking about a signal in its entirety, signal in its entirety, signal in its entirety. Then the output must be 0. When we say a signal is 0, we're not talking about just one instance in time. When I say x is 0, that means x of t is 0 for all t. That's what it means. When I plot it, that's what I get. Okay? That's what it means to be looking at a 0 signal. So something like this, where you have a particular t naught at which x is 0, that doesn't make this signal 0. Yeah, you can't possibly have a question about this. Just pulling your leg. Go ahead. Oh, no. Okay, let's call this x hat. Let's do that. Sorry about that. Yeah. So let's say the input signal is the scaled version of some original x hat. And then the output signal will have to be scaled correspondingly. So regardless of what x hat is, if I multiply it by 0, I'm going to get a zero input signal. And a property of linear systems is that you can view any zero input signal as a scaled version of some other signal that's not necessarily zero. When I say a signal is not zero, that means there's at least one instance in time for which x of t naught is non-zero. That's all it means. Okay? But linear systems have the property that if you give them a zero input, you get a zero output. This property, zero input, zero output property, we amorously call ZIZO, and it's a characteristic of linear systems. You've got to be very clear about the direction of the inference here. So if a system is linear, it implies that it has the ZIZO property. Okay? If a system is linear, then it satisfies the ZIZO property. In other words, the moment I tell you a system is linear, you say, okay, I know one input-output pair. 0, 0. That's always an input-output pair of a linear system. Okay? The arrow going the other way does not hold. In other words, just because you have a system for which zero input produces zero output, that doesn't mean that it's linear. Let's codify that. Just because you find a system. Oh, let's make it a little crisper. Just because a system satisfies the ZIZO property, doesn't mean it's linear. Can you give me an example of a system that takes zero input and produces zero output, but it's not linear? Y equals x squared or x cubed. In other words, the system that takes a signal x where y of t is the pointwise square or cubic power of the input. Such a system clearly is not linear, because you can easily show that if you scale the input signal by alpha, by what does the output scale? Alpha squared. So this is not a linear system. And yet, a zero input signal will produce a zero output signal. And that's why it's important for you to realize that this arrow does not hold. Okay. Last time we did an example where I said, okay, we're looking at a system that takes an input signal x and modulates it, let's say with cosine omega naught t, and it produces an output signal, y. Okay, that's my system. What did we say about the linearity of this system? It's linear. We showed it's linear last time. fact, this is generally true with even if this function here is not a cosine. So let's make this f of t, x of t, y of t is f times x. So similarly, this system is linear. Let me change this a bit. So now I have a system that has a modulation stage but then it adds another signal. This is my system in the red box. Okay? Where G is not 0. What that means is that there's at least some value T naught such that G of T naught is not equal to 0. Okay? Talk to your buddies and let me know what you think about the linearity of this system. You're seeing this system. I understand the TAs should have covered this in discussion. Okay, meatball. This guy. Tim. Okay, so Tim says, well, you should expect 0 output for what kind of input? So if x equals 0, then what's the output? Wait, Tim. G of t. In other words, y equals g. We've already said g is not 0. There's at least one point in time for which it's not 0. So 0 input produces a non-zero output. And we know that if a system is linear, we know. If a system is linear, then it must be Zizo, which means this is logically equivalent to if a system doesn't satisfy the Zizo property, then it must be not linear. And now we've shown that the system doesn't satisfy the Zizo property. So this is not linear. This system not linear. Now that's kind of strange. Well, it turns out not all nonlinearities are created equal. Some are more nonlinear than others. So this is not a hopelessly nonlinear system. Think of your high school days when you thought about straight lines. Here was x, here was y. You had straight lines that went through the origin, okay, where y was f times x, where f was the slope. Constant. Okay, I'm not talking about functions here. This f is a number. So you had lines that went through the origin. When x was 0, y was 0. Okay? This would be the analog of this system here. Except now we've generalized it to functions of time. So this is the counterpart. So this is from high school. This would be the counterpart of y of t equals f of t, x of t. Now when we say x is 0, we mean an entire signal is 0. And when we say y is correspondingly 0, it means y is viewed as an entire function of time is 0. Now, compare that with, again, high school, where you had straight lines that had a y-intercept. Same slope. In this case, y was f times x plus g. When x was 0, you'd get the y-intercept. It wasn't 0. Okay, so this is the counterpart of y of t equals f of t, x of t plus g of t. It's still a straight line, but according to our strict definition of linearity, it doesn't satisfy the Zizou property. So we consider systems to be linear that have this passage through the origin. And passage through the origin when x and y are signals mean that x viewed as an entire function of time is 0. That means it's 0 for all time. And y is correspondingly 0. Now, there is something to be said. Now, this is still a straight line. Right? It's not a parabola. It's not a cubic. Right? It's still a straight line. So what is it that distinguishes this kind of a system, or this system, from the system above? There is a way to use superposition to figure out the response of a system for the total response of a system when you have an input and when you have a signal that models some kind of other dynamics that's going on. So for example, if you have a capacitor that's initially charged, if I don't apply an input signal, an input voltage source to the circuit, let's say I have a resistor and a capacitor in a loop, okay? Even if I don't apply a voltage source and I just let the circuit go, the capacitor is going to have an initial voltage that's going to discharge, and so there's going to be a non-zero current through the circuit. Let me draw that. Here I have X, a resistor, a capacitor, initially charged. I don't care when you take the time reference for this circuit. Even if I turn this voltage source off, the charge in this capacitor is going to dissipate through the resistor. So there will be a non-zero current through the resistor. I'm not going to go into the details of what the equation is for this. But you can imagine that if there's an initial voltage on this, even if I short this voltage source, make it as just a straight wire, it's going to create a current until all the charge in the capacitor is gone. Now, what if I have a situation where I have both the voltage source and the capacitor that's not charged? How do I figure out the total response? Well, that's where I apply superposition. So I can figure out the total current at any given time by zeroing out the charge in this, assuming that there's no charge on the capacitor. So the charge on the capacitor will produce a contribution to the current that's modeled by this G. And there's a contribution from the input coming from here. So if I want to find the portion of the current Y, the output, that's only due to the capacitor and not the voltage source, I set the voltage source to 0. What do I get at the output? G. Now, you want to find the contribution just from the voltage source, assuming that so you assume that the capacitor is uncharged. So you set G equal to 0 and figure out what the response is. And then the overall total response will be the sum of the two. So it still satisfies some kind of a superposition principle. It's just not Zizo, like the other case. These kinds of systems we call incrementally linear. So a system like this is called incrementally linear. Why? Well, if I give this system an initial signal x, a first signal x input, the corresponding response will be f x1 plus g, right? And if I want to write it in terms of explicitly in terms of time, y1 of t is f of t x1 of t plus g of t. Okay? Now, suppose I give it, instead of x1, I apply another input. I call it x2. The corresponding response will be f of t x2 of t plus g of t. Okay? What happens if I apply a signal? Now apply x, which is x1 minus x2. What do you get? Figure it out. What's going to be the response due to that? It's not a trick question, and it shouldn't take you very long. Tim, point a finger. No. You get to pick. Overzealous kids. We go from this guy. Sam. Okay, Sam. You cancel out the what? G. Uh-huh. x1 minus x2. In other words, y of t is f of t times x1t minus x2 of t. Notice the relationship, which is, of course, y1 of t minus y2 of t. Notice the relationship between the difference between two input signals and the corresponding output signal. Now, this looks more like this system here, right? So incrementally linear systems behave linearly in terms of differences between input signals. incrementally linear system behaves linearly in terms of differences between input signals. Yeah. That's right. But look at this. If I have two different x's, x1, x2, right? And I have y1, y2, right? This becomes my origin when I take one of these as a reference. And I have a line that goes through the origin. So this is actually not the response. Maybe the confusion is that I'm not saying that this will be the response due to this signal. But you can model. This represents a linear system in its own right. In other words, you just have an offset. In the case of the high school line, the offset was a number. Now, in this case, the offset is a signal, G. That's all that it means. So it's not as bad as, for example, y equals x squared, where you can't model, where you don't have a relationship like this. You won't have a relationship like this if y is equal to x squared. But this can be viewed as a linear system. It's exactly like the other case. Yeah. Okay, let me rephrase. I understand the confusion. Yeah. Let me write it this way. Difference between outputs y1 and y2 is a linear function of the difference between x1 and x2. You're good now? So when I look at y1 minus y2, that is linear in terms of x1 minus x2. So if this causes confusion, ignore that. And just think of it this way. So it doesn't mean that when I send x1 minus x2, I'm going to get f times x1 minus x2 out. That's not what I mean. So if that's what is that what I said? Oh, no. This is not how the system behaves. Sorry. So I actually scratched this. This is what I mean. When you look at the difference between two inputs, it's a linear function of the difference between the corresponding. When you look at the difference between two outputs, that's a linear function of the difference between corresponding inputs. That's what it means. This property won't hold for a system such as y equals x squared. Yeah? Yeah, so that's also not appropriate. What I mean here is that y1 minus y2. Now I understand fully what the confusion was. y1 minus y2 is that. Yeah. Bonsai! Okay, take a break. Okay. Let's get back to work. So let me just clean up this act. Instead of saying now apply, say now look at. So you look at the difference between two outputs, and you see that it's a linear function of the difference between the corresponding inputs. These kinds of systems, which we've also called incrementally linear, are also called quasi-linear. So let me just write that here. Incrementally linear systems are also called quasi-linear. In some quarters. Now, I want to give you a little bit more of an abstract definition of systems. Remember, the view we take of systems involve input signals, output signals, an input signal space, and an output signal space. We say that the pair xy is a behavior of the system technically it's the input-output behavior of the system. If x is in capital X and y is equal to f of x. Okay? So x equals 0, y equals 0 is a behavior of every linear system. That would be an example. Example. Let's make that explicit. X equals 0, y equals 0 is a behavior of any linear system. Now, most systems don't have just a single input and a single output. Most systems have a whole set of these behaviors. And we can represent that with this script B. The set of all behaviors is a set of all ordered pairs x, y, where x is in the input signal space and y is a function of x. And this, of course, has to be in capital Y. Okay? A linear system then. So is this clear? Just like a graph of a function, except now you have, instead of the ordered pair being one scalar and another scalar, for example, now you have an entire signal and an entire signal. So in a graph of a function, you had t f of t, right? That was an ordered pair. And the set of all these, t was in the domain, and y of t equals f of t was in the range. This was the graph of a function, graph of f. Right? You had a set of ordered pairs. Here you have, so this B, the set of all behaviors, is the counterpart for the graph. Now you have x as an entire signal, y as an entire signal. X is some signal picked from this capital X, this bag of input signals, and y is a function of that x. So let me bring this down. Linear systems. If x, y, a linear system is a system such that if x, y is in the set of behaviors, then alpha, then alpha x, alpha y is in the set of behaviors, and if x1, y1 is a behavior, and x2, y2 is a behavior, then then x1 plus x2 and y1 plus y2 is a behavior. Right? So if you take any input-output signal that's a behavior of the system, you scale the input signal, and you scale the output signal, you get another behavior of the system. And if you take any two input-output pairs, x1, y1, and x2, y2, which are behaviors of the system, then if you add x1 and x2, and correspondingly add y1 and y2, you get another behavior of the system. So this is characteristic of linear systems. This is the show-off version, when you want to impress somebody at a party. Yeah?
So B is different for every system, right?
That's right. So different systems will have different B's. Right. Now, although this theoretically is a way to completely characterize a system, for practical purposes it's impossible. Because you can't exhaustively write all the possible input signals you can apply to a system and the corresponding output signals. So this is not a practical way of describing a system. This is just a theoretical, abstract way of describing a system. And it's not even the only way to describe a system, because in this course, we take the input-output view. There are signals inside the system. So in this course, we view a system as a black box. A signal goes in, a signal comes out. And it's just the input and output signals that we look at. And we call that a behavior. In more advanced courses where you study state space representations of systems, you open that black box and look inside. It's kind of like you have a box with an electronic circuit in it. You don't care what's going on inside, what the currents are and what the voltages are. You just care about one input port and an output port, and that's all you care about. It turns out stuff can happen inside that won't be visible if you put a black box around that system. And you may get smoke coming out of the box without you ever knowing what's wrong. from the input-output view. But we don't get into that in this course. In this course, we just care about the input and the output. And the system is kind of like a black box. And so when we describe the behavior of the input, or the set of behaviors, it's just an input-output pair, a set of input-output pairs. Okay, so I think that's about all I wanted to say about linearity. Another important property is time invariance or shift invariance, if time doesn't happen to be your variable of interest. This, again, has a very intuitive description. A time-invariant system behaves in the following way. If I give the system an input now, and I observe an output, that's an input-output behavior. Now, suppose instead of applying the input now, I wait 10 seconds from now, and then I apply the input. If the corresponding output is identical to the original output, but delayed by 10 seconds, and if this property holds regardless of the delay or advance in terms of how much I shift the input signal, then the system is called time invariant. You can think of a resistor. So a shift, I'll say it in layperson's term. A shift in the input, I should say a time shift, not an amplitude shift. A time shift in the input produces an identical time shift in the output. Let's again look at the resistor. I have a voltage source X hooked up to a resistor. The current is Y. So we determined that Y of t was X divided by R. Okay? The current through the resistor is the voltage across the resistor divided by the resistance. What happens if I apply, instead of X, the signal X hat, which is related to X by a time shift? This resistor doesn't care what we call the input signal. What's the corresponding output? I call it Y hat. How is it related to X hat? It's what? Forget about X. Just talk to me in terms of X hat. X hat over R. Okay? Now, we plug in the relationship between X hat and X. X hat of t is X of t minus cap t. Divided by R. How is this related to Y of t? Shifted by cap t. So Y hat of t, which is X of t minus cap t over R, is equal to Y of t minus cap t. In other words, shifting the input signal, this is not necessarily a delay. It can be an advance depending on the sign of capital T. If capital T is negative, that means we're advancing the input signal. But a shift in the input signal created a corresponding and identical shift in the output signal. So a resistor is a time invariant system. Or at least this model of a linear resistor. I should say this resistor. Now all I have to do is change the system a bit. Remember when we discussed linearity, let me put the explicit time dependence here. When we discussed linearity, I said all the system properties that we're about to discuss are idealizations of the real world. In the real world, there's no such thing as a constant resistance. You change the temperature in the environment of the resistor changes. So in the real world, the resistance will be a function of time. No longer a constant. So now what's the relationship between the output and the input? X of t over R of t. Okay? Can you tell me if this system is time invariant? What happens if I shift the input signal? What's the corresponding output? You've got to be very careful about what you shift. I'm just shifting the input signal. This system takes whatever I give it as the input signal. In this case, I've called it x. Now I've got to call it x hat. And divides it by R of t. So what's the output here? X hat over what? R of t. And x hat is x of t minus cap t divided by R of t. So that's y hat. Okay? Let me go to this board. Now you think about whether this y hat of t is y of t minus cap t. What is y of t minus cap t? That's what you have to compare it with. Huh? What's y of t minus cap t? X of t minus cap t divided by R of t minus cap t. So when you want to look at the shifted original output, every place you see a t, you have to replace it with a t minus cap t now. So you got to do it in the numerator and you got to do it in the denominator. And is this equal to y hat, which is x of t minus cap t over R of t, equal to for all time? Are they the same? No. Right? No. So this resistor is a time varying system. Roughly speaking, a system whose parameters, the system is defined by a set of parameters. The resistor in the first case was defined by a parameter, namely the constant R. If a system's descriptive parameters don't change as a function of time, that system is typically time invariant. This is a very crude definition. But the moment you see the parameters of a system, in this case the resistance, change as a function of time, that means when you look at this circuit now, as opposed to 10 minutes from now, because the resistances are not going to be equal in general, you're looking at two different systems, essentially. the system now behaves according to some value of r, and the system 10 minutes from now will behave according to some other value of r. And so the properties of the system change as a function of time. And that's what we call a time-varying system. Let's look at another example. Modulation. I want you to think about, don't blurt it out, think about whether modulation is time invariant or time varying. Whether this signal f is a cosine or not doesn't matter. So all I'm going to say is that f of t is not constant. Think about the case where f is constant also. So is this system time invariant? Talk to your neighbors. Okay, who was the last victim? Sam? Well, you got to make your eye contact so they know whom you're talking about. Is he the one busy, buried his head in his paper? Sorry. You are? Matt. Max. Time varying, Max says. How do you show it? Use my hat trick. X hat is x of t minus cap t. So you shift the input signal. Corresponding y hat is wait. This system takes any input signal you give it, in this case x hat, and multiplies it by f of t at any instance in time. So how is y hat related to x hat? Don't shift when you're not allowed to shift. F of t times x hat, which is f of t times x of t minus cap t. The system doesn't care what you call the input signal. Whatever you call it, x or x hat, at any instance in time, it takes that signal at that instance and multiplies it by f at that instance. So whether I call this x and that y, or this x hat and that y hat, doesn't matter. The system doesn't care. The system takes whatever I give it at any instance, multiplies it by the instantaneous value of f, and produces the instantaneous value of the output. And now we know that since x hat is related to x by this shift, the output y hat is written this way. Now when you look at y, shift y. If you get the same answer, then the system is time invariant. If you don't get the same answer, the system is not time invariant. So what do you get, Max? What happens when I take y and I shift it? You shift both the f and the x. In other words, you take this equation, every place you see a t, you replace it with t minus cap t. That means you have f of t minus cap t and x of t minus cap t. Are these two equal? If f is not a constant signal, they're not equal. If f is a constant signal, then just becomes a scalar multiplication. Obviously, that's time invariant, just like the constant resistance. Okay? So this is time varying. Huh? Then you would have a periodically time invariant system. That's something you'd study in a graduate course in linear system theory. Yeah. But a time invariant system must have this shifting property that y of t, that the output corresponding to the shifted input is equal to the shifted output of the original one for all shifts t, not just for a set of t's, capital T's. This must be true for all shifts. No matter how much I delay or advance the input signal, the output signal must correspondingly delay or advance. Question? Very good question. A capacitor or an inductor may or may not be time invariant or linear, depending on whether the capacitor has an initial charge or the inductor has an initial current. If the capacitor has no charge, then it's both linear and time invariant. And you'll explore all this in a problem set where I have, yeah, very good question. I mean, that's exactly the kind of questions I'd like you to ask. If a capacitor has no initial charge, if it has an initial charge, you already know the answer. We've done the quasi-linear system, right? But we haven't discussed its time invariance. If the capacitor has an initial charge at time 0, if I shift the input signal, the portion that is due to the initial charge doesn't get shifted. So you can imagine the system is not time invariant. But if the capacitor has no charge, then clearly if I shift the input signal, the corresponding output signal will shift. And you'll work through this, the actual integral that relates the current and the voltage of a capacitor in a problem set. Yeah? Yeah, but it happens over a duration of time. It happens over a time interval. Right? I can always model the change in resistance over a time interval. It doesn't change instantaneously. Right? It has only one value at any instance in time. It doesn't have multiple resistance values. That's why I can put a time dependence on it. What the cause of that time variation is, I don't care. The cause of that time variation may be that you're sitting there and you keep replacing the resistance in the circuit. Or it can be that you keep fiddling around with the AC and taking the temperature up and down and changing it as a function of time. The fact is, what I observe in terms of the system is a resistance that changes as a function of time. And that's how I make my measurements. Yeah. Now, the best part, there are other properties that I will discuss later. But now I want to, oh, I forgot to do this. Let's see. So let me define a system that's a time shift with a d tau. Okay? And instead of putting the x, I'm going to abuse our terminology and put the t in here. What's going to come out, this is a time shift system. What's going to come out is x of t minus, well, I've used capital T, so let's just use capital T. dt. X of t minus cap t. This is a simple delay or advancer system. Okay? It's a system. It takes the input signal. It's a function. It either shifts it to the right or shifts it to the left by capital T. Okay? A time invariant system is a system which doesn't care when you send in the signal x, whether you first shift the signal and send it through f, or send it through f and then shift. So if I have x of t here, x of t, this will be x of t minus cap t. This will be f of x as a function of time, which is y of t. Let's not call that y of t, then we're confused. And then you shift it. So you have y hat of t is equal to f of x, that. And this is f of x t minus cap t. T. Don't worry about the exact expressions. A time invariant system is a system that doesn't care whether you first delay the signal, in other words, create x hat, and then send it through the system. So you get, actually, this should be y hat. Let me clean this up before you get all confused. So a signal that we shifted, we called x hat. When we sent the shifted signal into f, we call that y hat of t, which was f of x hat evaluated at time t. Then we looked at the original system. You had x of t going into the system. You got y of t out. And you send it through a delay. You get y of t minus cap t. All right, now it looks good. If y hat of t is y of t minus cap t for all input signals and all shifts cap t, then the system is time invariant. In other words, you can reverse the order of the shift and the system. If you can do that and get the same output, the system is shift invariant. So we take the signal x, we shift it, we get x hat. We send x hat through the system, just like we did in the other examples. We send x hat through the system, we get a corresponding signal output, y hat. Alternatively, we take x, we first send it through the system, so you get y. And then you shift y. And you get y of t minus cap t. If these two output signals, corresponding to these two scenarios or configurations, are the same, and they're the same no matter what input signal you give it, chosen from the input signal space, and no matter what the shift, then the system is time invariant. So if y hat is y of t minus t for all x in x and all shifts, then f is time invariant. That's the upshot. And we'll do some, so just to give you a roadmap, next time when we reconvene, I'm going to look at systems that have both the linearity property and time invariance. Linear time invariant systems, LTI systems, they will be the bread and butter of what we're going to talk about in this class. And they have very interesting and nice properties. Go away.